Hello everyone, and welcome back. This video is going to be focused on solving exponential equations. So the past several topics have been involving exponentials. We talked about what are the graphical features of an exponential equation, what are some applications of exponential equations, but now we're finally going to get to actually solving exponential equations. And solving exponential equations is going to be a little bit different than solving any other type of equation. So before we even get started, I want to remind us about what type of language we use when we talk about exponentials. So right here it says that this is our first type of equation, and they are equations with a common base. So I want to remind you that a base is really just the number that's being raised to an exponent. So if you look in example number 1 here, you can see that I'm raising 2 to the x plus 1 on the left and 2 to the 9 on the right. So 2 would be my base. Okay, on the right of the page, I have number 2 has a base of 5 on both sides because 5 is the number being raised to the exponent. So basically, there are 3 steps to solving exponential equations. You're not going to have to do every step in every problem. For instance, the step right here, there's basically only one step that you have to do. But basically, the first step is you have to check and see if either side of the equation can be simplified. So because these are sort of our simplest equations, there's not going to be anything to simplify. But let's say you had 2 expressions on one side of the equal sign. Let's say you had 2 to the x and you also had 2 to the x plus 1. When I say simplify, I mean that you have to use exponent laws in order to combine that all into one expression. And so we learned that the rule for if I'm multiplying these two terms times each other is that all I have to do is add the exponents together. So I could take 2 to the x plus 1, or in other words, 2 to the 2x plus 1. Right? And that's just an example. Again, we aren't doing that on this page, but for future reference, that's what step 1 means when it says simplify each side of the equation using the properties of exponents. Step number 2 says rewrite the equation so both sides have the same base. We will get to an example of that in a minute. But if you are looking at these examples, and it literally says in type 1, equations with a common base, that means both sides do have the same base. But let's say that if my base over here was 2 and the base over here was 4, I would have to rewrite it so that both bases are the same. And again, I will teach you how to do that on a future slide. Because I don't have to do 1 or 2 here, I've already sort of checked off those steps just because this is a simpler version. I get to skip right to step 3. And step 3 is a step you'll always have to do. And that is that you drop the bases and set the exponents equal to each other. So what I mean by that is these 2's go away, and I literally just take the exponent from the left, and that becomes the left side of my equation, and the exponent from the right, and that becomes the right side of my equation. The reason I can do this is, look, if both sides of my equation have a common base, both of them are 2, I know the 2 sides of the expression will equal each other if the exponents equal each other, right? If the right side is 2 to the 9, if I make the left side also 2 to the 9, they're going to be the same as each other. So if the base is the same and the exponents are the same, essentially you have the same expression on both sides. So I'm just going to solve this new equation that I wrote just from the exponents. And again, this doesn't work until you have a common base, but once you have a common base, which I do in these problems, you can set the two exponents equal to each other. And then from there, you just solve here. The left side just has x plus 1, so I'm just going to go ahead and subtract 1 from both sides, since that's the opposite of adding. And that leaves me with x equals 8. I'm going to do the same thing on this second problem. Again, I have the bases are the same as each other, so I'm just going to write an equation where I set the two exponents equal to each other. And what that is going to leave me with is 4n plus 5 is equal to n minus 7. Okay. Right now, I have a variable on both sides as well as a constant on both sides. I want to get all the variables onto one side, so I'm going to go ahead and start by subtracting n from both sides. That will leave me with 3n plus 5 equals negative 7. And then I want all the constants on one side, so I'm going to go ahead and subtract 5 from both sides to get the 5 away from those n's. That gives me 3n equals negative 12. And last but not least, I have a multiplication here, so I'm going to go ahead and divide to undo that multiplication. And that leaves me with n equals negative 4. So now we're stepping it up a little bit. If you look at these equations, we do still have a common base, so we're not going to have to worry about that quite yet, right? Like every base on this first equation is the same, they're all 3, but the sides are not totally simplified. So if you look at this left side here, we see 2 different expressions. One expression is 3 to the k, and the other expression is 3 to the k plus 2. And I'm going to need to use exponent laws in order to combine those two. Now again, remember, and I briefly touched on this on the last slide, but our properties of exponents tell us that if we have x to the a times x to the b, I can simplify that as x to the a plus b. Okay, so essentially, if I have the same base in both expressions, I can combine them into one expression by keeping the base and adding the exponents. So here I'm going to keep the base of 3, and I'm going to add the exponents. So I have k, and then I'm going to add that to k plus 2. And that is just equal to the other side of the equation. I don't know why I put the equal sign all the way up there. But the other side of the equation was already simplified, so I just leave that as 3 to the 5k minus 1. On the left side, I can go ahead here and I can simplify or combine like terms within this exponent. So I had k plus 2. K plus k, that gives me 2k's. So really this is 3 to the 2k plus 2 equals, equals 3 to the 5k minus 1. And then now I'm at the point in the problem where I can take those exponents and I can set them equal to each other, right? Because I already have a common base, so I don't need to rewrite the base. I've simplified both sides. I'm ready to continue. So now I'm on step 3, set the exponents equal to each other. So that gives me 2k plus 2 is equal to 5k minus 1. Again, I want all the exponents on one side and all the constants on the other. I'm going to move the exponents to the right side because 5k is bigger than 2k, and I like dealing with positive numbers, not negative numbers, just me personally. You could move them to either side. You will get the right answer either way. And I'm also just in this same step, because I'm running out of room, I'm going to go ahead and add 1 to move all the constants onto the left side. And that gives me 3 is equal to 3k. From there, I can divide both sides by 3, and it leaves me with 1 is equal to k, or k is equal to 1. Doesn't really matter which way you write it. But yeah, then that is our answer. I'm going to do the same thing with equation number 4. Again, you'll notice that I have 2 expressions on the left side. I only have 1 expression on the right side, so the right side will stay as is. But the left side, I'm going to have to add those exponents and keep the shared base. So it becomes 10 to the negative 1 plus 9. Okay, negative 1 plus 9, I'm just adding 2 numbers there, so I can go ahead and simplify that even further, and that would give me 10 to the 8 is equal to 10 to the v plus 4. At this point, you'll see I have a common base on both sides. Both sides are totally simplified. So again, I'm at step 3, set the exponents equal to each other. So 8 is going to be equal to v plus 4. Oh no. Not plus, that's equal. Okay. 8 is equal to v plus 4. And then this one is actually relatively simple to solve. The only thing that's in the way of v being alone is this plus 4. So if I subtract 4 from both sides, that already takes me to my answer of 4 equals v. Okay. So moving on, we're stepping it up one more time. But so basically, just as always, I'm going to kind of start working through the steps. So first step is simplify each side. I can look at both sides of this equation. I'm looking at this first one on the left. Both sides look pretty simplified to me. 4, really can't make that simpler than 4. And 2 to the x plus 6, there's not really anything I can do there. So already good on step 1. The next, step 2, says rewrite with the same base. Now, this is not something we've had to do before, but look at the 2 sides of this equation. You can see on the right side, I have a base of 2. If you look at the left side, you might think there's no base at all. There's no exponent there, which is true. There's no exponent there. Don't know why I said exponent, really weird just a second ago. But there's no exponent there. But you could think of this, right? Everything basically has an imaginary exponent of 1. So this is like 4 to the 1. So essentially 4 is your current base. Okay? Nobody's going to be writing this as 4 to the 1. It's just 4. But essentially 4 is our base. But I don't want 4 to be my base. I want 2 to be my base. So when I say rewrite with the same base, I'm looking to have a shared base. Most commonly, that will mean the base of the smaller number. For purposes of this class, probably the smaller number will always be the base. There are instances where that wouldn't be the case, but I can explain that later. But for now, we want the base to match whatever the smaller base is, which is 2. So I would still have 2 to the x plus 6, but I want to rewrite the left side of my equation with a base of 2. So I want this to be written as 2 to some exponent, and that's me rewriting 4. So I would figure out what exponent do I need to substitute in to make this expression right here equivalent to 4. And that would be 2 squared. Okay. If you don't know your exponents really well, this could get a little complicated when it comes to some problems with bigger numbers. So if you're ever unsure, once you know the base you want, this base of 2, just figure out how many times do I have to multiply it by itself to get to my desired number. So if I multiply 2 times 2, that gives me 4. So since I multiplied twice, then I know 2 is my exponent. But most of you probably don't even have to worry about that with the smaller numbers at least, because you would just recognize that 2 squared is the same as 4. Once I have gone ahead and rewritten with the same base, I can go ahead and solve just like I did before. The reason I have to rewrite with my same base, why that's so important, is because you know how I keep setting the exponents equal to each other? And the reason that I can do that is because if I have the same base to the same power, I know that's literally the same thing. Well, if the left is just 4, like 4 can't have the same exponent as 2 and have the two sides equal. So we need to have the same base so that having the same exponent actually makes the two expressions equal to each other. So I'm going to move on here, and we are going to go ahead and take those exponents and set them equal to each other. 2 is equal to x plus 6. I'm going to subtract 6 from both sides, and that gives me negative 4 is equal to x. Now with these problems, and I didn't do this before, if you ever want to check your work, you can always go back and do that. I can go ahead and plug negative 4 in for x. So I could check and see, do the two sides of the equation equal when I rewrite this original equation, but instead of x, I write negative 4. Okay. So as I simplify the right side, that would become 2 squared, and 2 squared does in fact equal 4. So since I'm getting 4 is equal to 4, that proves to me that I did this correct and I got the right answer. So I do highly recommend that, especially if you're ever taking a quiz, right? You wouldn't want to make a mistake that you could catch and not catch it. So I would highly recommend that you do go ahead and check your work in that way. Okay, moving on to the second question now. Here we have 5 to the 3x minus 1 equals 25. Once again, both sides are simplified, right? There's not two expressions on either side. There's one expression on the left and one expression on the right. But the base on the left is 5 and the base on the right is 25. So what I need to do is I'm going to take the side with the smaller base and I'm just rewriting that side. But the other side I need to write with the common base. That common base is 5. So I have to figure out 5 to what power gives me 25. And that would be 5 squared. It's not always going to be squared, okay? But I guess I was just starting off with some simpler examples. But again, the reason that 5 squared works is because 5 times 5 gives you 25. At this point, we are going to go ahead and we have simplified each side. We have rewritten with the same base, so I'm ready to move on to step 3, set the exponents equal to each other. And I'm going to take 3x minus 1 and set that equal to 2. It's a nice two-step equation here, so we always have to start with the addition or subtraction, and I add 1 to both sides. 3x equals 3, and then I have a multiplication, so to undo it, I'm going to divide, and that leaves me with x is equal to 1. And now we have our last slide here, and we're going to work through these steps again. So, step 1, simplify each side. Well, I'm going to look at my example here. Both sides look pretty darn simplified to me. There is only one expression on each side, so there's nothing I have to do there. So step 1, already done. Step 2 is to rewrite with the same base. So I'm checking, do they have the same base? Well, on the left, my base is 9. On the right, my base is 3. Well, those are not the same numbers as each other, so I do not have the same base. So what I'm going to have to do is I'm going to have to rewrite the base of 9. So the base of 3 comes along for the ride. On the left side, I have to rewrite 9 as 3 to some exponent. So 3 squared happens to give me 9. So I rewrite the 9 as 3 squared. But if you notice, this expression also already had an exponent. So this isn't something that happened on the last slide. So if that's the case, basically I'm rewriting 3 squared as 9. Okay. And so I'm putting that in parentheses as if, right, originally it was the 9 was being raised to 2x plus 6. So since 3 squared represents the 9, I'm just going to put it in parentheses and say that I'm raising that to the 2x plus 6 power. Now, if I have a base raised to a power raised to another power, for instance, x to the a to the b, we learned this in our last unit. This was our exponent law here, is that results in you taking the common base and then multiplying the exponents. Right? We talked about this again with the exponent laws. You basically do one step simpler than what is on the page. So in the last example, we were multiplying the two bases, so I had to add the exponents. Here, I am taking an exponent and raising it to an exponent, and so I'm going to multiply the two exponents, because that is one step simpler than an exponent. So I rewrite this again, and it's now 3 times 2, and then 2 gets multiplied times 2x plus 6. And be really careful, the 2 is being multiplied by this entire quantity, so I'm putting the quantity in parentheses. Gives me 3 to the 2 times 2x plus 6. And on the other side, I still have 3 to the 2x. Okay. And then you could go ahead and simplify this exponent and multiply, or in other words, right, we're going to distribute this 2 to both terms inside of the parentheses. So I would have 3 to the 2 times 2x is 4x. 2 times 6 is 12, so 4x plus 12 equals 3 to the 2x. Yeah, that's supposed to be next. And then it's time to set them equal and solve. I'm going to kind of come off to the side here because I'm going to run out of space at the bottom of the page, but 4x plus 12 equals 2x. I'm going to go ahead and bring the 2x over to the left, so I'm subtracting 2x from both sides. When I do that, my left side is 2x plus 12. And on the right side, everything went away, so that essentially leaves me with just 0. Then I'm going to move my constant over, so I'm going to subtract 12 from both sides. That leaves me with 2x equals negative 12. And then I'm going to divide both sides by 2, which leaves me with x equals negative 6. So, apologies that work got a little messy. I didn't leave myself enough room. But hopefully you were able to follow along with that. If you didn't totally quite get that yet, we do have one last example before I end this video, so try to pay attention to this last one. Again, my first step in this list of steps is to simplify each side. I look at both sides. Left side, this is only one expression. Right side, this is only one expression. So nothing to simplify there. Step 1, check. Now I need to rewrite with the same base. So as I'm looking right now, I see a base on the left of 4 and on the right of 16. Again, I'm going to go ahead and rewrite that smaller base. That's the base that I want to keep. And I need to rewrite the bigger base in terms of that smaller base. So I need to say 4 to what power gives me 16. Okay? And it just so happens that 4 squared gives me 16. So I'm going to rewrite the 16 as 4 squared. And I'm putting it in parentheses to remind me that this 4 times 4 to the second power is replacing the 16. So before, the 16 didn't have to be in parentheses because it was just a number. It wasn't an expression. But now that I'm replacing 16 with this expression of 4 squared, I'm going to put it in parentheses to represent that that whole expression is being raised to the y minus third power. Okay. Following along with my exponent laws, when I go to simplify, I'm going to have to multiply those two exponents times each other. So I'm going to have to multiply 2 times the quantity of y minus 3. When I go to actually solve that, what I'm going to have to do is I'm going to be distributing the 2 to the y and the minus 3. So the left gets rewritten as 4 to the y plus 2. The right gets rewritten as 4 to the 2y minus 6. And then from there, I can go ahead and set my exponents equal to each other because I finally have my common base. And y plus 2 is equal to 2y minus 6. Once again, I'm going to do two things in one step here because I'm running out of space, but I want all the constants on one side, so I'm going to go ahead and subtract y from both sides to get rid of the y from the left. And at the same time, I'm going to move the constant from the right over to the left by adding 6 to both sides. And that ends up giving me 8 on the left and y on the right. So my final answer is 8 is equal to y. So at this point, we've looked at several different types of problems where you are solving an exponential equation. The steps that we performed on each one were different, but keep in mind, if you aren't sure which steps to follow, you can always use this same list. So while you don't always have to do every step, these are the list of steps for you to sort of work through. So first, check and see if you can simplify anything on either side of the equation. If you can, go ahead and do that. If you can't, keep moving. Okay. After that, go ahead and check both sides and say, do they have the same base? If they do, great, keep moving. If they don't, take a minute and rewrite each side with the same base. Once both sides are simplified and have the same base, you go ahead, set the exponents equal to each other, and then you can solve. And that is how you solve exponential equations.